So I'm hoping to finish up the SystemVerilog lecture today. So far, we've looked at, I did a demo last time where I did simulation, wrote SystemVerilog and simulated it in ModelSim. And we also did synthesis. I actually deployed a design on the board and showed it to you. I don't know how well you were able to see it, but yeah, basically we made an adder. We're going to talk more about simulation today because I'm going to cover Testbenches, which is a way you can automate the testing in simulation, basically by writing one SystemVerilog module that tests another one. And then we're going to talk about always statements today, which is really the last component of SystemVerilog we're going to cover. So far we've talked about behavioral and structural modules. So far the only behavioral code I've showed you was the continuous assignment statement, which is that assign signal equals, right? And then the structural Verilog is where you instantiate and connect some modules together, right? And the way you connect them together is through signals that you declare as logic, right? And so you can connect one module to the other by having the same signal connected to the ports of both, right? And that's effectively drawing a wire between them. So the continuous assignment statement is treated as a blob of logic. So you have an equal sign, you have a left-hand side and a right-hand side. The left-hand side is the output. So you want to be careful that you don't double drive the output, right? So only one assignment statement, or only one driver per signal, right? And then the right-hand side are the inputs, and anytime any of the inputs change, it causes the assign statement to trigger, to update its output. And that's the secret behind concurrent semantics. If you can understand that, that's the most important thing to understand about HDL. So it doesn't matter what order the lines of code are in your module, because each statement is sort of like, it has a set of triggers, a set of inputs, and then anytime any of those inputs change state, change values, it will immediately cause the output, or the left-hand side in this case of the assignment statement, to update. Okay? And then I showed you, there was a simulation of that. And then this is the structural Verilog, where the difference here is that we've got, well, at least in this is the structural part, because we have a module called myDesign where we instance a module of type and3 and then wire it up. In this case, we're just wiring it to these internal signals. You guys with me? Mm-hmm. So far it's pretty simple, right? I mean, that's really all we've covered. Is there's the module line, and there you can build a kind of a block diagram schematic using structural Verilog, or you can do an assignment statement.
I have a question.
Yes?
Can you name, instead of N1 name in the previous slide, can instead of having N1 logic, have Y logic and then the Y, or it will cause an error?
If you mean
No, in my design part.
Down here?
Yeah, if instead of N1 we had Y.
Oh, sure. Yeah, you could name it. You could name it if you had a signal in here that was called Y, sure, you could call it Y. Yeah. Okay, then we talked about how to represent numbers. Is this clear? Everyone comfortable with this? Okay, so you got a bit width. You're supposed to specify the bit width, apostrophe, the base, and the value. And then we talked about bit manipulations. Verilog makes it easy to concatenate bits together with a curly brace. You can do duplication with a double curly brace thing. And of course, you can also do slicing, where if you have B bracket 15, N bracket, that'll take out bit 15 in B, right? Okay, and then we covered simulation. Now I went through this really fast because I know that in lab you guys are, Charles and Philip are showing you additional examples of how to do simulation. Of course, you're going to be doing it, in there, and you'll be able to ask questions. So that's Okay, so one thing I want to point out here, though, is when I simulated last time, I used a series of commands to set up the inputs to the design I was testing. Specifically, I used the force command. These commands are actually, this is actually a script in a language called TCL, which stands TCL, stands for Tool Command Language. And you can set up like a simple script to change the inputs of something in order to see how the outputs change. And so it's kind of a quick and dirty way to test something. So there's only a few commands you have to know. Restart-F just restarts the simulation, which means that it makes the simulation time, it puts the time back to 0. Also, the restart will reload a design that you've recompiled. So if you're testing, updating your Verilog, and then testing again, you'll make the change, vlog it, compile it, and then restart it. Right? You don't need to restart the entire model sim or anything like that. I know some students do that when they're new at this. They think they have to restart all of model sim whenever they make a change. You don't have to restart model sim, you just restart the simulation with restart-F, okay? But if you forget to compile, then your changes won't take effect. So you still have to compile your design. So you change your design, you compile it, restart the simulation. Then you've got these force commands for forcing values. And then, now this syntax is a little strange. This is force data in. Notice I have a capital X with quotes. This is actually Verilog syntax. The capital X stands for hex, but you can also use, I'm sorry, scratch that. This is VHDL syntax, but you can also use Verilog syntax, which the equivalent for that would just be to say this is 32 bits, because this is 1, 2, 3, 4, 5, 6, 7, 8. There's hex 8 digits here, and it's in hex, so this implies that this data in is a 32-bit signal. So in the Verilog notation, you would just say 32 apostrophe H 0, right? So this is just, the TCL allows Verilog and VHDL syntax for these. I used to use VHDL, and this script is an old example. And then run. So run advances the simulation. So generally you'll do force, run, force, run, force, run, and then in this case you would be looking at the output of your waveform to check to see if it's what you expect it to be. Obviously that's a horrible way to test, because it'd be better if you could have the script also check the outputs for you, which is what test benches are good for. All right, but this is just like I said, this is kind of a quick and dirty way to test something. So yeah. Sometimes you want to test something before you write a test bench for it. Okay, then I showed Quartus. I'm going to skip over that. Okay, so now let's, like I said, we're going to move on to the last idiom of Verilog that we'll cover in this course, and that's the always statement. The always statement is a way to create behavior that's a little bit more nicer than just using an assign statement, a continuous assignment statement. And so you can use, I don't know if you guys noticed this, but when I do the assign statement, I've never showed you like an if statement or a loop, right? Because you can't use if statements and loops inside your module. And if you want to use those, you have to put them inside of this always. You have to enclose them inside an always statement or an always block. In other words, what I'm trying to say is that if you want to use conditional programming constructs, you have to put them inside of an always block. Okay? Now here's where things get a little confusing with this. An always statement is acting like an assign statement. It just gives you a little bit more flexibility for how you can express the behavior. Okay, so what that means is that, remember I said with an assign statement, whatever the left is on the left-hand side of an assignment statement, that assign statement is driving that signal. Like that assign statement will own whatever signal it's driving. And with an always statement, it allows you to basically create a multi-line assign statement. But anything, and you can have multiple outputs in there. You can set multiple outputs, but whatever outputs you set in there are then owned by that always statement. That always statement becomes a blob of logic, just like it's essentially like an assign statement. You guys with me? So in other words, you can't have two assign statements that both output to the same wire, or you'll double drive it. That's what I think that's a much simpler way to state that. Yes?
But what about three way of red when we have question mark and column, and we use it as simulation multiplexer, but it can be also used kind of if logic. Yeah,
so that's exactly right. You could do the same. You can create a multiplexer with an assign statement, in which case you can use an if statement instead of the question mark. Although I think the question mark is a little bit more convenient for multiplexers, actually. I prefer to use that. And so you're going to find yourself having a choice sometimes where you can use an assign statement or you can do an always statement, right? It's up to you how you choose to do that. I prefer to use assigns whenever I can, just because they're simpler. So let me go into some more details here. So there's actually three things you'd want to use an assign statement to do. By the way, these are also called processes. In VHDL, they're called processes. And the reason I mention that is because in Model Sim, they're always called processes, whether you use Verilog or VHDL. But there's three things you'd want to use them for. One, as I was just explaining, you can use them for doing complex combinational logic. Now remember, an always is only, sorry, not always, assign. An assign is only for combinational logic, right? So if you want to put like a case statement or an if statement or a loop, but you still want it to be combinational logic, you still want to create, Boolean logic or like a lookup table, then you can put that in an always, and in this case you're going to use always underscore comb is the way that you start it, and then you put either one statement in there, or if you have more than one statement, you put a begin and an end, right? Which is kind of like your open and close curly brace in Java or C. And I'll show you examples of that in a minute. So again, first reason for using an always statement would be for complex combinational logic. So the 7-segment decoder that we're asking you to do for Lab 2, for instance, is combinational logic. But it's kind of complex, right? Because there's a whole bunch of, you're building a decoder, right? And you've got 16 possible outputs, and the outputs are 7 bits and the inputs are 4 bits. Now, can you do that with an assign statement? Yes. In fact, some of you might have already done that. You can just use an assign statement with a little question mark operator, and you can build your whole 7-segment decoder in one assign statement, right? Or you can use an always statement, in which case you can put a case statement in there, or a switch statement. You guys know switch statements, right, from Java. In Verilog, they're case statements. Same thing, right? And case statements / switch statements are also good for doing like a 7-segment decoder. You could do it that way too. That's up to you, okay? Now another reason why you'd want to use an always is if you need memory or sequential logic, because you can't implement sequential logic or memory in using an assign statement, right? So this is obviously, if you want to do a flip-flop, a register, a RAM, you don't have a choice but to use an always for that. And if you do that, you're going to start that one off using an always underscore FF standing for flip-flop, which is kind of a misnomer because you might be creating a RAM, not a flip-flop, a RAM, but you still have to use always underscore FF. Okay? Guys with me? Now, here's the part that's a little weird. If you use always comb, then there is an implicit sensitivity list, meaning that the always statement will activate, much like an assign activates when any of the inputs change. an always an always statement will change whenever any of its inputs change, where the inputs are basically any signal that are used as inputs in the always statement. So like if you have if A equals B, well, the A and B would be inputs. Or if you say C equals A plus 1, well, then A is an input, right? But if you create an always underscore FF, you have to explicitly give the sensitivity list, because whenever you have memory, you can have inputs that change that actually don't activate that always statement, right? So in the case of, like for example, if you have a RAM or a flip-flop, you might say always underscore FF at, and then you would say pause edge clock, meaning it's a rising edge, sensitive to the rising clock. And I'll show some examples of that here in a minute. I'm just giving you kind of just a top level overview right now. Okay, and then the third thing, I'm going to come back to number 2 here. Number 2 is sometimes you want to create things that you don't even intend to synthesize into hardware. Like you just want Verilog to behave as a regular programming language. Like for example, for Testbenches, right? And you have to use an always for that, right? So the 3 things are complex combinational logic, anything that has memory, or Testbenches, basically, or test harnesses. Testbench is kind of like the test harness and the thing you're testing, the design under test, right? The test harness, the thing that's driving the inputs, setting the inputs, the thing that you're using instead of typing force in model sim, that would be also implemented in an always statement. You guys with me? But you have to be careful, because that means there's some things that you can do in an always statement that immediately disqualify it from being synthesizable. There's certain little features you can put in there, like if you put a delay, you tell it to delay for 5 simulation cycles, that immediately disqualifies it. That means you can run it in a simulator, but you can't put it on the FPGA. Okay? Okay, so let's look at some examples now. So like I was saying, and this actually answers your question a little better. So here's an example where I say assign out1 equals, if select is 1, then take foo and put that into out1, right? Or set out1 to be whatever is in foo, right? If select is 0, then take bar and assign it, or assign out1 to bar, right? So this creates a mux where bar is input 0, foo is input 1, and cell is a selector, right? I can rewrite this into an equivalent form using an always underscore comb by saying always underscore comb begin, and in this case I have begin and end here, even though I don't even need it, because this if statement is one statement. Begin and end is used if you have multiple statements. So in this case, this is actually redundant, although it's usually a good idea. It's a good practice to put them in, but I didn't actually need begin and end here. So always underscore comb, and then I say if select, then out equals foo, else out1 equals foo, else out1 equals bar. So this is doing exactly the same thing as that. It's just written a different way. Yes?
When I want to compare some bus to the value, let's say in binary, do we use 1 equal or 2 equals? Two equal.
Well, okay, that's a good question. So use 2 equals. I'm going to make sure I say this right. 2 equals will test if 2 values are equal. However, if either one of the values or both is a z or an x, it will still be false. So in other words, if you have 2 inputs that are both z, they're both floating, and use double equals, it'll say false, even though they're both z, or if they're both x, right? And you might say, what is the point of that? Because double equals, in that sense, you're doing a hardware double equals. Now, if you use triple equals, then it's used more for test benches, where it'll actually evaluate to true if the 2 sides of the triple equals are a non-binary, like a x or z, right? That's the difference. In this class, it usually never comes up, so I wouldn't worry about that. But yeah, there is a difference there. Okay, so just to clarify, the reason for that is because in real hardware you can't test for equality for floating signals, right? Or an unknown signal. That doesn't make any sense, right? You can't say if these signals are both unknown, evaluate the equals to, the equality to true. Well, no, that doesn't make any sense. Right? But sometimes you might want to do that for testing. Okay. Okay. So why would I do the always and not instead of the assign? I don't know. I wouldn't. I would just use the assign in this case. I think this is much more elegant than that personally. But if you end up with something like that's more complex in terms of the number of options, like the 7-segment decoder on the other hand that you guys are doing for lab 2, you might want to use an always com, because doing the 7-segment decoder as one of in this structure, would be many levels of nesting on this ternary operator. You might think it looks ugly. I wouldn't. I mean, I think that I'd probably do the 7-segment decoder with this assign myself, but it's up to you. You might be more comfortable with using an if statement. Okay? Okay, so the other thing though about this is you have to be careful. I want to point a couple other things out here too. So in this case, cell, foo, and bar are inputs. Any change to those are the sensitivity list. So any changes to those will cause out1 to be triggered. Down here, same thing, except it's a little bit less obvious what your inputs are because they're kind of embedded in this if statement, right? But it's the same thing. If any of these guys change, it's going to trigger the always statement. Now, obviously, with an always statement, you can have more than one output, too. That's another advantage versus an assign statement. Assign statement is one output, whereas down here, I could set multiple things inside this, multiple outputs. Yes?
Is there a way for switch case for always com?
I'm sorry?
Is there a switch case for always com?
A switch statement?
Case? Yeah.
Yes, yeah, there is. Yeah, I'm going to show you that one. Yep. I'll show you an example of that. I already said that. Okay, so one of the things I want to mention here is you have to be careful that with an if statement, you have a control. You're introducing control, which means that there's a potential for the always to activate because one of its inputs changes, but then have it not set all of its possible outputs. So what I mean by that is imagine if I didn't have that first line of code here, right? Say I just say always com, and I said if select equals 1, out 1 equals foo, right? If you do that, and you set select to 0, then it will never drive out 1. It will never set out 1, right?
So it would be X?
No, actually what it'll do is, well, this is a little confusing. Normally, it would create a latch. It would leave out, like if you activate an always and you don't set out 1, it'll assume that you want to keep out 1 to be whatever it was before the always was activated, right? And that will create memory. That'll create a latch. A not very good memory, though. You don't want to create latches. It's better to have edge clock triggered memories instead of a latch. And hopefully you guys talked about latches a little bit in 211. However, what will end up happening in this case is because we're using an always com, the compiler can possibly recognize that you've got a latch behavior in there and it'll give you an error. It'll tell you, oh no, you need to make sure that you set out 1 in any control path through this guy, right? So in this case, notice here I set out 1 as I set it to a default as out 1. I set it as bar, and then I changed it to foo. Now this one actually causes it to change because the effective output will be whatever the last setting of the output was after this thing activates, right? So you can use this style where instead of putting an else here as I had before, you can set all your outputs as default, and then below them you can reassign them if you want, and you won't actually see them, you won't see a glitch or anything because you reassign them. It'll be the final assignment. That's kind of weird, right? That's a little strange because you guys are used to, like, if you write language in like Java, if you change a variable, you'll actually potentially see it change. Whereas in this case, you won't actually see, if select is 1, you'll activate this always, it'll set out one to bar, and then it will change it to foo, but in the simulator, it'll look as though it always had just set it to foo, right? Yes?
So in always comp, if we drive same signal in multiple statements, it will end up with the last one.
Yes, exactly. So that, yeah, and that's a good point. That sort of contradicts what I told you earlier. I said, don't make sure you don't double drive any signals. You can, if you do that in an always, you're not double driving it, you're just changing your mind because it's happening within the always block, right? Why? Because this always block is one blob of logic. It gets converted into one circuit, logic circuit, right? Right? So yes, if I do this, I'm not double driving out 0. It looks like I might be double driving it because you're setting it twice. But I'm setting it twice within the always block. And this always block owns out 1, and that's okay. You can change it within there. But if I had another always block and I set out 1, then it will be double driven. You'll get a short circuit there potentially. So yeah, that's kind of, that part's, I think, takes a little while to get used to that concept. Okay. Oh, by the way, I tried this today because I forgot. So I went in and I wrote an always comb, and I had it only drive an output on one outcome of an if statement. And it's funny, what ends up happening is it'll work and ModelSim will take it. ModelSim's like, fine, and it'll just create, and it created a latch. But then I took the same code and I compiled it in Quartus, and Quartus was like, no, you can't do that because it's not, what you wrote was not combinational. You said it was going to be combinational because you put always comb. You promised me this would be combinational logic, and you put a latch in there. So this is an example of something ModelSim will be okay with and Quartus won't be, which is kind of unfortunate. We got two different compilers that behave differently. Okay, so here's these, no, sorry, I thought this was a switch statement, but it's not. This is an example of having multiple outputs in an always comb. So, yeah, this is pretty much just, this is kind of, actually this is, I don't know why anyone would do this, because you could just do the same thing with assign statements. You know, I don't know why anyone would put that in an always comb. Yeah, but basically it's 5 outputs, one always statement. Okay, and here's the case statement. So this is what I was alluding to earlier, and this is actually a 7-segment decoder. So case, now the syntax here is a little different. It's not switch. You start out with case, but then you just put each case in with a colon, right? So data is the input. This is only 0 to 9. The one that you guys are doing for Lab 2 also includes A through F. So this is only accepting a value, a decimal value, 0 to 9, and then it's translating that into the 7-segment code. So you can use this as a template. One thing to keep in mind, though, is that this one, I think, if I remember correctly, this one assumes that the 7-segment display is active high, and you guys are doing active low. So you have to invert all these bits. And also, the other thing is, I think the A segment, which is the top segment, I think in this one it assumes that's the first digit, the most significant digit. So I think the bit ordering is, I think the bits are not only inverted, but they're also backwards, right? So, but I don't remember that for sure, but I think that's what's going on in here. But it's okay, because if you want, you can use this same, you can use as an example. You're probably just going to have to fix the output. Yes? There's no need for breaking the end of each piece. Yeah, I was going to mention there's no break statement. Yeah, yeah. But if you have multiple, you have to use begin and end on these guys. If you have multiple, if there's multiple statements you want to associate with each of these cases, you have to use begin and end. I don't have begin and end on these because there's only one statement. Now also notice it says end case. So I have case, end, case. It's kind of like module, end, module. But it's just begin and end if you want to put more than one statement inside there. So that basically, it gets translated to like a big if then else. There is a default too. Yeah, there's a default as well.
Is it required?
It's required if it's the same rule as before. If you assign segments on every possible value of the input, then you don't need the default. But in this case, I didn't do that, because what happens if the input is A through F, right? So that's why I put the default. So basically, if you put A through F in here, then it's going to spit out zeros, which in the case of the DE2, this will light up all the segments. But I think in this assumption, it'll turn them all off. Okay, so that's just it's just the syntax. And to be honest with you guys, I always have, whenever I write Verilog, I usually have to refer, like if I want to do a case statement, I have to go back and look up the syntax, because I don't always remember it. One of the purposes of the slides is to provide you with a reference for the syntax. Okay, now here's a little different form of the case statement. There's also a case Z statement, and this is pretty cool, because you can put don't cares in here. So in this case, you can say, well, if the first bit is 1, I don't care what the next 3 bits are. I want to take that first case, right? So
that is useful for priority decoders.
Exactly, yeah. Yeah, so that's kind of neat. I think there's actually a few other variations. I think there's a case X and a case Y. You can look them up, but in this class I just present the regular case and the case Z, and the only difference is the case Z allows you to put question marks to denote don't cares. It doesn't come up very often though. Okay, so that's complex. Those are examples of using an always statement for combinational logic. So always _ com. You don't have to specify the sensitivity list. You just say always com, and the compiler will infer the sensitivity list based on the inputs inside the always statement, whatever you treat as an input. Okay, so now let's talk about sequential logic. We'll talk about memory, behaviors with memory. So in this case, I'm going to build a flip-flop, a D flip-flop, and I hope you guys covered flip-flops in 211. So a flip-flop is a usually 1-bit memory element, but in this case, I'm actually got 4 bits. There's 4. It's kind of like having 4 single-bit flip-flops in parallel, like an array. Yeah, it's a register. Yeah, sometimes you just call this a register because it's a multi-bit flip-flop. Now, what's a flip-flop? A flip-flop is a memory element that changes on a clock edge as opposed to a clock level, right? So it's an edge sensitive, meaning that basically the output will always be the same. It will never change until you get a clock edge, at which point during that clock edge, the flip-flop will basically take a snapshot of whatever the input was at that time. It'll sample the input, and then it will put that input onto the output, and it will hold it there until the next clock edge, right? So you notice that the syntax here is really simple, and that's done deliberately because these registers they're used very often, just like the multiplexer with the little question mark. You will have a whole lot of these registers inside your CPU because you're going to have pipeline registers in there that are going to be holding values from one cycle to the next. So you want to make sure you're comfortable with this. So the syntax is easy. It's always _FF, and then now I have this additional thing I have to put after the always. I have to put the sensitivity list. In this case, I say @ symbol, and in this case, I'm saying pause edge clock. It means that activate the always statement on the positive edge of the clock, which is the rising edge, right? And then I just put D into Q, right? Meaning that D is not, if this was a combinational logic, D, because it's an input, would be in the sensitivity list, right? But in this case, it's not, because I explicitly want to basically block D until there's a clock edge. So I want to ignore D unless there's a clock edge. So always always FF at pause edge clock, right? And of course, you could have neg edge clock, which is the falling edge, but in this class, we just pretty much always use the rising edge. Now you can also put a comma, and you can have other things in the sensitivity list too. And I'll show you some examples. But in this class, generally speaking, it's just usually just clock and potentially a reset signal. Okay, so yeah. So now the only thing you might have noticed here is, now notice there's no begin and end because there's only one statement, right? Also notice, why is that less than equal? Less than equal. Why is that? That's a alternative way to do an assignment inside of an always statement. This is called a non-blocking assignment. And I'll talk in more detail about that in just a minute. But just for the time being, just assume that's just an assignment. Yes?
Just a question. Why you mentioned that it's better to have pause edge clock rather than level? Like if clock is 0, assign, and if clock is 1, don't share.
If you do it that way, it'll be a latch. You know, you can make latches, in fact, there's an always underscore latch for that. And you might say, wait a minute. If the sensitivity list combined with the code that's in there defines the behavior, then why do I have to say always flip-flop, always latch? I mean, shouldn't it infer that? Yes, that's how it used to be actually in Verilog. It would just, but the always underscore FF is supposed to protect you, because that way you're telling the compiler to expect that this should be a flip-flop. And so if you accidentally make a latch, and how would you do that? Well, if you just leave off the pause edge, right? If you forget to put the pause edge, this will instantly become a latch, in which case, I think so. Maybe I'm wrong about that.
If clock 1, then assign.
Yeah, if you said if clock 1, that's right. Yeah, you'd have to also say if clock 1. But anyway, if you screwed something up, then the compiler would give you an error, and you want it to give you an error because you accidentally wrote behavior you didn't intend, right? So that's what the always underscore FF is doing. You could just say always and leave off the underscore FF, but then you're putting yourself at risk. You know, it's risky, right? Because then SystemVerilog introduced this underscore FF thing that is a safeguard, okay? But anyway, you asked why not use latches. Latches are harder to meet timing with latches. And so basically, essentially your design will be slower. If you, that's kind of the simplistic way to explain that. It's a lot more complicated than that, but basically you'll have a slower clock. Your clock rate will be slower if you use latches. Okay, so here's another example. Now, by the way, notice I didn't point this out in the last slide, but notice I've got a module line where I've got these top-level inputs and outputs that feed into this guy. You don't need that. This is creating a whole module just to create a flip-flop. In reality, you probably wouldn't do this unless you were really unless you really like to break your design into modules, right? Normally, you would just take this always and you just put it in somewhere in your larger module, right? You guys with me on that? Does that make sense? So basically this whole module is creating a flip-flop, but you don't have to build a whole module for a flip-flop. You could just take this always block and insert it wherever you need a flip-flop, right? Because remember, you can mix together, you can have multiple always statements, and you can even mix that with structural code too. You can have behavior and structure mixed together, right? Some people might argue that that's not a good practice, but I think for a small design, it's not a big deal. Anyway, so this is an example of a flip-flop with a reset. So it basically just says if reset, then reset it, right? Otherwise, don't reset it, right? Now, this is a synchronous reset, though, because the reset is not in the sensitivity list, which means that I have the functionality to reset this guy, but it's not going to reset until there's a positive edge of the clock, right? So this is a synchronous reset. Now, you can also have an asynchronous reset, which you can change by, all you have to do for that is just add the reset in the sensitivity list, which means that if the reset goes from low to high, it will activate the always, even if there's no clock edge, meaning that you can reset it whenever you want rather than having to wait for the clock edge. Yes?
So always underscore flip-flop makes OR for its sensitivity list and triggers if any of the...
Yeah, as a matter of fact, you can actually type OR in here too. The syntax, I use the comma, but I think in the original Verilog spec, it actually was, you had to actually type OR inside there. There's different options. I'm only showing you like one dialect of Verilog. Verilog has, and SystemVerilog have different ways to accomplish the same thing. Okay, I think that's, yeah, so that basically just creates a flip-flop. Now you might say, should I use a synchronous or an asynchronous? Yeah, it's up to you. It's up to you. Sometimes it matters, usually not. Sometimes there's some corner cases in your design where having a synchronous or asynchronous could make a difference. Okay, here's another example where we have an enable and a reset. So in this case, we basically add an enable where even if you have a pause edge clock, it won't actually update Q unless there's an enable. So this would be useful if you have a register in your design that you only want to write under certain conditions. Is it, in the enable would be a control signal coming from your control unit, right? So in other words, if you don't have an enable and you have a clock, obviously your clock keeps going, right? So if you don't have an enable, all the flip-flop is doing is delaying, the D, the Q is the 1 cycle old version of D, basically, right? If you always enable. If you have, if you're always, updating Q, right? If you don't have an enable. But if you have an enable, this allows you to hold the value of Q longer than 1 cycle, right? So that would happen like I don't know if we do that now in the RISC-V. In the MIPS processor, we had these 2 registers, high and low, that were only changed if you did a multiply or divide instruction, right? And so we would use that for that, but there is no version of that anymore in RISC-V. RISC-V did away with that. I guess we might not need the enable actually in this design. I don't remember. There might be a case where we need that. But that's up to you. That depends on, you can add those features by updating the behavior. Okay, so let's talk about blocking versus non-blocking. So I brought this up earlier. There's this non-blocking is less than equal and blocking is equal. This gets, this is kind of confusing. This still confuses me sometimes. Okay, so the difference is, well, one way to think of this is a non-blocking assignment statement will update the output internally right after the assignment is made internally. So in other words, if you have something like this where N1 gets D and then Q gets N1, right? You have this data dependency here, right? Because you update N1 and then you change N1 and then you use it as an input on a line below that, right? If you use a non-blocking, then the version of N1 that's seen in this second line of code is the old value before you wrote in that first line of code, right? So basically what this means is if you use non-blocking, the outputs don't actually get applied until the always finishes completion. It finishes, gets done, executes all the lines of code, right? So that way, if you were to do this, and this comes up a lot, this is a common thing. If I say D goes into N1, N1 goes into Q, the synthesizer will actually interpret this as a shift register. It'll interpret this as, it'll consider the N1 as an internal connection, a serially connected 2 flip-flops, right? Which means that, basically D will go into N1 after 1 cycle, and then after the second cycle, it'll appear on Q. So this will create a 2-cycle delay between D and Q, right? However, if you use a blocking assignment, which is a regular equal sign, then it'll enforce this data dependency. So when it sees N1, this N1 will be updated reflecting what happens after the first line of code, right? The problem is that this code does nothing, because if you do this, this ends up just becoming a single flip-flop, because N1 is effectively the same as D. So this is the same as just saying D goes, Q gets D, right? Make sense? This is redundant. So this will give you it'll work, but it won't give you this delay behavior, this serially connected behavior, right? Now you might argue, wait a minute, why not just do the blocking and change the order of these 2 lines of code, right? Wouldn't that fix it? Yes, I think so. But here's the convention. The convention is whenever you write sequential logic with an always statement, you should always use non-blocking unless you really know what you're doing, right? If you write combinational logic, use the blocking, right? So if we go back now, let's go back and look at these slides now. All of the slides I showed you that were a flip-flop, they all use this equal statement. But if I go back to where I was showing the combinational logic all uses this equal sign, and that was intentional. Now you can use either one, but you can run into trouble. Now, the reason I say that is because the blocking versus non-blocking actually extends beyond the internals of an always statement. Here's where things get tricky. So as it turns out, the non-blocking thing can happen if you have multiple always, separate always statements, right? And one always writes something that the other always reads. You can get into trouble if you use the blocking assignment statement. It'll act funny. You won't get the delays that you expect. And this happens a lot in your CPU design when you have pipeline registers, where you have, in one cycle you want to advance the instruction in the instruction register, and in the next cycle you want to get it through the register file. If you want to create this pipeline behavior, make sure you always use this non-blocking. I know that's kind of vague, but I've run into trouble when I've accidentally forgot that and used this. Yes?
So just to summarize, if we want assignments happen one by one, we use non-blocking. If we want them to be simultaneous, we use blocking.
Right. Yes, exactly. Yep. But like I said, by convention, remember, if you're doing memory, use memory including flip-flops, registers, or RAM, use non-blocking. If you're doing combinational logic, use blocking. By the way, I hate this. I hate this. VHDL has the same thing, but they do it so much nicer in VHDL. In VHDL, they have something called a signal versus a variable. And so if you want to get this blocking behavior in VHDL, you have to declare the signal as a variable as opposed to as a signal. To me, that's a better solution. In other words, VHDL uses different data types to deal with this problem, whereas Verilog relies on the operators, which to me, I think that's confusing because it's very easy to make a mistake and use the wrong one. Okay, so I think I always said that, right? Use always a flip-flop and non-blocking for synchronous logic. Use continuous assignment statement to model simple combinational logic. But if you want to have a more complex combinational logic, then you can use an always comb, okay? And don't assign the same signal twice in two different always statements. All right, good. All right, so the last topic here are test benches. I wonder if I have time to do a little demo of that. Probably not. Okay, I'm going to go into test benches. I was thinking about trying to do a little demo of those shift registers, but I want to make sure I get through this. Okay, so Testbench is having Verilog test Verilog, basically. So the design that you're testing is called the DUT, the design under test. The other design that's testing the DUT is the Testbench. Now normally the DUT sits inside of the Testbench module. So the Testbench module usually, there's obviously different ways to do it, but in my experience the Testbench is usually a module that has no inputs and outputs, and it contains the design under test. So the design under test is wrapped up inside of the Testbench. Make sense? The Testbench's job is to provide stimulus, signal stimulus, input stimulus to the design under test, and then usually it also checks the outputs as well, automatically. And if there's an error, usually prints an error message, and then basically the Testbench says, help, I need a human involved here, because there's an error, you need to fix something, right? So the Testbench won't fix the bug, but hopefully it'll notify you that there's a bug. That's the idea. Okay, now there's different ways to do test benches. There's there's a million ways to do it. Everyone does it their own way. In this lecture, I'll show you 3 different ways to do it. There's a simple test bench that actually just sets the inputs, doesn't check the outputs. Then there's a self-checking test bench that checks the outputs. And then there's a self-checking test bench with test vectors. And the advantage with the test vectors is that you don't have to embed the inputs and outputs inside the test bench. You can provide those as a separate file. So the test bench just reads a file and uses that to figure out what to use as the inputs and what the expected outputs are. You guys with me? Mm-hmm. That's the test vectors file. A little bit more complicated because you have to start doing file I/O with Verilog, but that's a very common way to do it. Okay, so So let's say we have this design called silly function. It has 3 inputs, A, B, C, output Y, and it has one continuous assignment statement in it, Boolean logic. And we can create a simple test bench. Now notice that the test bench has no inputs and outputs. That's important because the test bench is responsible for acting by itself. It doesn't need any outside influences, right? Now the DUT, on the other hand, does. So the DUT has the DUT is instantiated in here, and then I use something called an initial block. An initial block is the same as an always statement. The only difference is it only runs once at the beginning. Okay? They're generally only used for test benches. Right? Sometimes we use them for initializing RAMs, which is, you can actually synthesize that. In fact, I think in this class we'll use them to initialize the program memory in your RISC-V processor. But in this case, we're using it for the test bench. So initial begin, this is a begin and end because there's multiple lines. You say A equals, well, notice there's a single equal. Use blocking for this. I don't think it matters though. But is using blocking for this. A equals 0, B equals 0, C equals 0. So we're going to set the inputs. And then we use pound or hashtag 10. This is a delay for 10 simulator ticks. Now you might say, what's a simulator tick? That's whatever you set up the simulator. In ModelSim by default, it's a picosecond. But it could be a nanosecond, it could be a second. It doesn't really matter. Whatever the simulator set up is to be a tick. Now, the minute you put this in, you immediately disqualify this guy from being synthesizable. Because you can't synthesize a delay. So this is purely for testing, purely for simulation. Now, you might say, well, why do you need a delay at all? Well, because combinational logic in Verilog is instantaneous. You put the inputs in, boom, it updates the output. However, you still have to put a lambda amount of time. It can't, you have to give it some non-zero amount of time to update the outputs, even though it can be infinitely small, basically, right? So what I'm trying to say is the purpose of this delay is you put a delay in between the time you set the inputs and the time you check the outputs, right? Now, I'm not actually checking the outputs. In this case, this delay will just give me the waveform. It'll just give me, it'll show me the waves. I'll see 10, every time I change the inputs, I'll see 10 units worth of the inputs being constant. Right, you guys with me? Okay, and then I change C. Now notice in this case, I'm doing a counting sequence. C is 0, I change it to 1, but I don't change A and B because I assume I want to keep those as 0, 0. Sorry. Okay, and then I go through all 8 combinations here of A, B, and C. I go through a counting sequence. Now, one thing you might have noticed here is notice how I instanced this DUT. You might notice there's no dots in there. There's no periods in there to connect the inputs to the outputs, and that's because I used the old, well, not the old style, but there's a thing you can do in Verilog where when you instance something, you can specify the connections, the port connections by order instead of by name. So you can do this. This is a kind of a shorthand. The only reason that works is because the input, it's A, B, C, Y in that order, right? So when I instantiate the silly function, I put A, B, C, Y. Because it's in the same order, I can connect the A, B, C, and Y from in here to the A, B, C, and Y that's on the ports, right? I don't recommend doing that, though. And I thought I had changed, I'd updated all those because I'd rather you guys don't do that because these Verilog, it's just a potential for making a mistake. It's better if you put dot A, open parenthesis, A, close parenthesis. Yes?
Those A, B, C, and Y are signals from Testbench model, not from inside the dot.
Yes, exactly, yeah. So that's oh, and I also forgot to update, sorry. This also needs to be updated. Let me change it right now. Sorry, I have the old dialect. These should be logics, sorry. And I'll just update this now. So, yeah, sorry. Dot C. Oh, I don't want it. Okay, there we go. Dot Y. All right, there we go. Yeah, sorry, I had an old, I'm trying to update these with the SystemVerilog dialect. Okay. All right. Okay, the problem with that though is I have to debug it with waveform. If I can add testing, I can add self-checking to this by just adding an if statement after each one of those assignments and delays. So I do the assignment and the delay, and then I check to see if y, the output of the dot, equals what it should equal based on my understanding of that, the way I think it should be working, right? And if it doesn't equal, then I can put a little display of $display, and I can say that one of the test cases failed. Now, by the way, $display is a built-in function that basically works like a printf. You guys know printf from C? And it'll just print that in the model sim console. You guys with me? Notice, by the way, this is the triple equal sign. Notice it says bang equals equals. Now you guys might think, why is there two? Like if you have not equal, it's bang equals, right? Well, it's bang equals equals because I'm using that triple thing I was telling you guys about earlier, where this is the type of comparison that will actually treat x and z as real values, even though in reality they're not. Okay. All right, so now let's make it a little bit more complex. So one of the problems is that delay. That delay is a kind of problematic. It would be better, instead of having delays in there, to synchronize the setting up of the inputs and the checking of the outputs. You can just do that on the clock. Use the clock for that. So we can assign the inputs to the dot on the rising edge of the clock and check the output on the falling edge. You might say, well, yeah, but that, I mean, doesn't it make it a little bit more complicated than it needs to be? Why not just put the hashtag, you know? I don't know. It's a good question. I don't know. This is just another way to do it, right? So the first thing we're changing is we're going to use the clock instead of the delay, right? You might not want to do it this way. You could still use the delay version if you want. Another thing we want to add is we want to create a test vector file. So instead of having to hard code, you don't want to have to hard code the inputs and the outputs into the design. It would be better if we can keep the design separate from the inputs and outputs. So a test vector is simply the inputs that you want to put in and the expected output, right? So we can store those in a separate file, which looks like this, just one test vector per line. I don't even think you have to put them on separate lines. I think any white space will do to separate these guys. But in this case, I've got one per line. And notice I put a little underscore here to separate the A, B, and C from the expected Y. Make sense? Okay. Okay, so then, again, this is, sorry. Somehow I missed these data types. These should be logics, not reg and wire. We had to update this. When we updated a SystemVerilog, one of the things that was changed was the data types went from being reg and wire to logic. And that was a huge improvement. So I recommend that you use logic here. Okay, here we go. So now we've got a test bench. Again, there's no inputs and outputs. But now we've got some other things going on here. We've got this thing called the test vectors. And this is actually a memory. And this syntax is really goofy, in my opinion, because basically it's a 2D array. You guys know 2D arrays. You've used them in Java, C++, right? But whenever you have a 2D array, the row always comes first, and the column comes second, if you think of it like a matrix, right? Mm-hmm. Row, then column. But in Verilog, when you declare it, you put the width of each entry first, in this case 3:0, which is the columns. It's the width. The horizontal goes first. The vertical, which is the depth, comes second, and it comes after the name, which is even weirder because, you guys, usually the two dimensions go right next to each other. Now, the way I remember this, though, is normally if you had a regular signal, the width would come before the name. right? But if you have a RAM, then you stick the depth of the RAM after it. So this is the opposite order, It's columns then rows, or width and depth. But that's basically, the fact that I have 2 dimensions there means it's a RAM. Yes?
So is it four test vectors, each one of 10,001 elements, or it's 10,001 test vectors, each of
10,001 test vectors. Now you might say, wait a second, you only have 4 bits. There's only 16 possible test vectors, guy. Why did you declare 10,001? Don't know. This is from the book. The book authors did that. Basically, the point there was, we'll declare as more than we need, because you might not know how many there are in the file, right? Because we're going to read the file. We have to declare that before we read the file. I don't think there's any way to, at least I don't know how to read the file to figure out how big the file is and then to allocate space after the fact. I don't think that's even possible in Verilog. So that, as a result, they just declared a whole bunch. Yes?
Can you have don't care sign in the test vector file?
I'm sorry?
Can you mention don't care sign?
You can put don't care. Yes, you can put X's. That's right. You can. Yes, you can. Okay, so then I also have this thing called vector num and errors. These are counters. You might say, if they're counters, why don't you declare them as integers? Why don't you declare them as bit arrays? Unclear. I don't know. Again, this is from the book. That's how they did it. They declared these as bit arrays. And then we've got the design under test gets instantiated. Again, they're using the old syntax here. Okay, then this is the neat part. Now, this always creates a clock. Now you might remember when I showed you this before, I created a clock in ModelSim using a tickle command where I said force clock and then I specified the period and the duty cycle. In this case, you can create a clock in your test bench by using an always with nothing after it. Now this is the thing that Charles ran into some issues with this in lab last week, because he used an always without anything after it in an example, right? When was an example of logic. So he was building combinational logic. He was showing an example where he was doing some combinational logic, but he didn't use always underscore comb. He used always, and it ended up hanging the simulator. The reason for that is because if you use always without an underscore com, it doesn't have any sensitivity list, which means it runs continuously. And so if you don't have any delays in there, it'll hang ModelSim.
So if there is no sensitivity list, each signal in a sensitivity list?
If there's no sensitivity list, it literally triggers as fast as it can trigger. It triggers constantly, right? Because there's nothing to trigger it, right? So in this case, though, it's okay because of this, the #5. So this will create a clock. It'll set the clock 1, wait 5, set it low, wait 5, then immediately re-trigger. Set it 1, low. So this is a real nice way to create an oscillating clock. And so this is another way to write the always. No comb, no sensitivity list. But be careful when you do this. This is only for test benches. Also not synthesizable. Now, Charles said, I was surprised. He told me today that when he did that, he actually put that into Quartus and he got it to synthesize, which surprised me. I wonder what was going on with that. Yes?
Why are you using blocking assignments here instead of non-blocking?
It doesn't matter. I think this is just conventional. Because it's not memory, they just use blocking. I don't think it matters, though. You could use either one in this case. I know that's a wishy-washy answer, but that's one of the eccentricities of Verilog, in my opinion. Okay, so now we're continuing. Now I have an initial statement, and now I use this $readmemb. I read the vectors out of example.tv. I'm going to read them into my test vectors file. There's an optional third parameter that tells it how many to read. In this case, they don't have that. I think you might get a warning saying, I was only able to read 16 vectors or whatever, but that's not a big deal. there's a readmem B and a readmem H. One assumes it's binary data. One assumes there's hex data. And then there's also a reset. Inside this initial, we also set reset to 1, wait 27 units of time, and then set it to 0. So the initial block is like the always block, except it only happens once at the beginning. So it's a good time to initialize your memory and to do your reset pulse, if you need one. Okay? And you might say, why do we need a reset pulse? We're testing a dang combinational dot here. Well, you need it for the counter, the test vector counter, which I'll show you here in just a minute. Okay, then I have another always that sets test vectors of vector num, and it assigns them to A, B, C, and Y expected. Now, I showed you guys this last lecture where you can actually put a concatenated form on the left-hand side of an assignment. I think I showed you this with an assignment before. This is not an assign statement, but same idea, right? So I'm going to set A, B, C, and Y expected. Now you might say, why Y expected? Well, there's going to be two versions of Y now. There's a Y coming out of the dot, and there's a Y coming out of the test vector file. The difference is one of them is the actual Y, and the other one's the Y that I expect there to be, right? So I'm going to be comparing those two. So for all the outputs of your dot, you're going to have to have an expected version and an actual version in two different signal names. And notice that this is happening on the positive edge. So remember I showed you that picture here where a positive edge is where the inputs get assigned. That's what's happening in that always that I just showed you there. That. Now you can have always at neg edge clock, which is where we're going to check the output. Then the whole reason I'm setting them on the rising edge and checking them on the falling edge, the only reason I'm doing that in this case is because it's a substitution for having that delay that I had before, right? Instead of putting delay like #5 or whatever #5, #5, this is a way to basically just synchronize the testing. You know, set it on the rising edge, check it on the falling edge. So now I have a reset, if not reset. If reset is high, basically don't do anything. Ignore all this. If reset is low, then you check to see if Y equals Y expected, and if not, you print an error and increment the error counter. That's pretty much it. You just check to see if they match, and that's it. So that's on the falling edge. And then this is inside that same always block, right? Yeah, I haven't. Continuing inside the same always block, you can increment the vector number, which only happens on the falling edge of the clock, and only if reset is 0, right? Because it's inside that the reset if statement as well. And then this thing is a little weird, but it says if test vectors vector num equals x. Because if I only have, like, say, 16 test vectors, but I've allocated 10,001, once I get to number 17, or the 17th one, right, which would be when vector num is 16, right, then it's going to pull out an x. It means I'm done. I've gone through all my test vectors. So if that happens, I can just display a thing that says, this is how many tests completed. Remember I told you the display is like a printf. It's a formatted, so you can do formatting. You can say how many, you can use vector num tests completed with errors, and then you can use this $finish that just stops the simulator. Now in Model Sim, it's a little obnoxious because if it hits that finish, it'll ask you if you want to close Model Sim. And if you say yes, it'll close Model Sim, and you won't ever get to see it if it printed like what it printed, right? Which is kind of obnoxious. But generally speaking, when you run these kind of test benches, you don't run them in a GUI. You just run them in a command line, in which case it's fine because you would just look at your console output. But the problem is if you run this in a GUI and then it hits that finish, it wants to kill the GUI, and the command line window is inside the GUI, all right? So you got to watch for that. But you can just say no. Just be aware of that. And that's, that's it. That's the test vector. That's the test bench. Wow, the timing was perfect. Great. So now you guys know everything you need to know for Lab 2. You guys have an example for you can do the 7-segment decoders as an if then else or as a case statement. The test vector is just, you can use this as a template for that. The test bench, right? And then of course you're going to be demoing this on the board. So when you run this on the board, you're not going to be synthesizing the test bench. You only use the test bench in the simulation, right? When you go to put this on the board, your top level design will be whatever your top level module is, right? And Charles and Philip will provide more details in lab.